So it's my pleasure to introduce the last speaker of the session, Jose Maria, who probably needs no introduction at all to this community, who will talk to us about conformational ensembles. Thank you.
Okay. Okay, the sound is okay? Perfect. Thank you very much, really, to the organizers, to you, for being here, for allowing me to share this meeting with you. It is the first time. I know CCP-EM for a long time, but it is the first time I've been such a meeting, and I should not have, but I am really impressed by the UK structural biology community. So I have changed a little bit the title of my talk. I'm going to talk certainly about conformational ensembles, about how we address them with cryo-electron microscopy, but I'm going to use a more general perspective on that and present you which is my view of where we are and what we may be doing in the future. Certainly, when I talk about conformational ensembles, I'm not talking about something that has been already in the field for almost 20 years, that is the type of analysis that maximum likelihood shows. When he was in Madrid, we were doing. It was, if you have really clustered data, you can use that a priori knowledge and go for this type of analysis. However, if you have other type of data in which the variability, the structural variability is more continuous, then you are violating the hypothesis on which we were based our method. So I'm going to talk about these other situations. And really it's a very timely topic in the sense that really the explosion, methodological explosion and the capabilities has started recently, although there is some pioneering work that didn't flourish to some extent, but really now it is coming up very strongly. The notion of discrete 3D classification and continuous classification, I mean, I suppose it's almost obvious, but here you would have an example of a discrete two-class classification with the case of the spike. This is what we would like eventually to have. How do we do it today? Well, yesterday you were listening to Amit Singer, a very nice method, the Recobar, to get the PCA components of 3D space in an elegant and fast manner. What have we done? Well, we have approached the situation from 2 points of view. One is what we call deformation fields, and the other, in the absence of better word, we describe it as heterogeneous reconstruction by artificial intelligence. What is deformation field? Deformation field is essentially you have an average or representative structure that you consider that the images you have in your study are going to be coming by some deformations of that 3D structure, a particular deformation for each of the image that you are getting. This is fantastic in many aspects from the mathematical point of view. It allows us to use AI and not AI approaches. However, if we are considering that you have a 3D structure that is being deformed, then we cannot do anything if on top of that you have an additional mass or a mass is missing. So the mass has to be constant. The heterogeneous reconstruction, on the other hand, is, as we use it, it has been defined to account for these cases in which we have this conformational variability, but on top of that, we have some compositional variability. If I start from the older work, it was published 23, and we keep working on that, what is the variability analysis through this deformation field? Well, we start, let's see, probably this. Okay, we start from this average reconstruction. This average reconstruction is modified in some flexible manner, and it gets a computer simulated image that you are going to be try to make as similar as possible to your real thing, that is the experimental data. So really, through changing the parameters of how this is defined, you try to understand how this average structure is deformed to get into, to produce the 2D image that is your input. And this is how we get into these deformation maps that has as many points as images, and we explore them by a number of tools. But essentially, what is here, what is there? I mean, we try to understand these conformational maps a posteriori. Of course, we could do something else, and it's not working bad at all. Is to say, listen, since I know the deformation field in each of the image, what about if I introduce the deformation field in the reconstruction algorithm, and I do something about sort of perhaps collapsing the landscape? This is essentially, you have also seen dynamite from short, is the same conceptual idea. It is working very nicely, especially when we put it in an iterative approach. And this was published also 2 years ago, but this data set is new, and we are still working on that. And is actually the power of working with the formation field with very good mathematical tractability in an iterative manner. But of course, we went into other types of analysis because for the complexity of what you can find in the cell, flexibility fields, thinking in compositional heterogeneity were not exactly what we needed, at least not only. So we went into the latest approach. You can find it. It was published this week in Nature Communications. And essentially, what we have gone is for a conceptually first approach, simple decoder, encoder, decoder, bottleneck architecture, where we have put many new things. We have put many new things in that we work in real space. So masking is very simple. We have changed completely the activation functions, and with the goal to obtain volumes or maps that have a higher resolution. I will get very briefly into that because the point I want to convey to you is the following. We have worked a lot in what we call pose and CTF entanglement. So about that, we have worked a lot into the activation function. Well, yes, the Siren activation function is the first time they have ever been used in the context of Cryo. They are particularly better than the one used so far, but I don't have so much time, so I have to choose one point. And I'm going to choose this one about the singularity of the method. I'm trying to go a little bit fast because I'm going to present you a number of things, and I also want to answer myself some of the questions that were posed before. Okay, which is the main idea that to me at least, is the following. Well, you have the decoder, encoder, decoder architecture. You normally would have an image. This is your hopefully conformational landscape, and you would have this point in conformational landscape. Perfect. Now, the new thing, this point is decoded into this map. And now we say, listen, what about if I now take many different projections of this map? I, of course, put all the CTF, the noise, whatever, and I come back here. This is projections of the same structure. So these points should be very close to the original point. So I put a constraint in latent space. And you can also imagine that this, I am reprojecting my volume. If I would have the reprojection already done, because I would be working with tomography, obvious. So is it important? Well, imagine this simple experiment, this simple ablation experiment. We take away this entanglement of the pose. You go in a simple encoder-decoder, you have this point. And now we are using a data set that is very simple, computer generated. It was from Slavish Ionic. It had to be a linear transformation, the one that relates the number of maps that she created. We created the projections there. We went to the map and we said, okay, so we should have a linear, we should have a straight line. Okay, I know that this is linearity, this is non-linear, but they don't understand at all this thing. I mean, really, it seems that our conformational landscape have many things that may not be conformational. After all, it depends where I'm looking at, or where I'm looking from. Excuse me for my English. I have more or less information about the variability I have a chance to discover. What about now if I use this approach of projecting in many different directions? That is a way to say I'm trying to get a conformational landscape that would be invariable with respect to the pose of your image. No matter which is the pose of your image, I would be able to give you the same point in conformational landscape. Well, we don't get in a straight line, but we get something that is much closer. So really, we are getting into the correct direction. But of course, how many methods have I mentioned? The AMIT, our two ones, sure. What about validating them? What about comparing them? What about to have a way to understand if we are saying the same or we are saying really the opposite? You can find most of the work here. Whatever you cannot find there is because we are answering the referees that are making a very good job. And soon, I hope you will see published with more data than what it is here. But what is the basic idea? When you have many methods, you have many input methods, different mathematics. Yesterday, it was principal component analysis, no AI. Now with AI, the two times I have used it. 8 dimension, 39 dimension. How do I compare these methods? Well, we thought, well, we don't see another way that to put all the methods into a common space. Okay, you have delayed the question one step. How do you make this common space? And this is the key. Very simple, very simple. This, we have said, this common space has to be such that when decoded, has to produce something very similar to the first original space, and when decoded with another decoder, should produce an output space that is very similar to the output space. So this bottleneck is rich enough to, okay, not give it everything, but give something very similar to your starting thing. So it's a good approximation of your starting thing. And on top of that, we have a pairwise minimization distance saying that all points from the, I mean, the cloud of points should be as similar as possible from the different input. With that space, now we have a very interesting tool to understand how similar and how non-similar results are we getting from different methods. Let's try first with something that by first principle should work. This is a very simple and very common ribosome data set. And here they are the point that when decoded into maps, they have not the ATS ribosome, but just the 60S subunit. So there is a compositional difference here. And then we compare the result with Wernicke, that is this way to deform the volume, and with Hetziren, that is also able to understand compositional variability. And what do we find? What do we expect? Wernicke 3D doesn't know anything about compositional difference. It couldn't. So the largest difference with Hetziren, of course, in the area where the difference is about this losing a subunit. For the rest, they are quite similar. So this is what we expect. Still, things are complicated because what I'm presenting you now is the case of a clustered, I mean, the spike of COVID, and is together with SID and Surimanian. This has a cluster structure with 1 up, 2 up, 3 up, and many things around, I know, but it's not continuous. And what we get is that with Hetziren and with Cryo Dragon, it's not exactly the same. We were taking as sort of ground truth the clustered approach, the discrete classification, if you want. And we see, of course, that the two methods are not provided the same. what can we do? Well, we can go for a sort of consensus space in which we get whatever is more common to those images that are locally clustered in pseudo conformational space in a more similar way. And we see that it's more related to the discrete conformation. But anyway, the message is we have the tool to now understand the different different spaces. That is not meaning that really the result we are getting with the different methods are coherent. We have a subset of images for which they are coherent, a subset that really they are working differently. And even worse, those images that are not treated equally by different methods, I cannot say which would be fantastic. I cannot say that they are rubbish. Not at all. This experiment really surprised me, and I don't have an answer. Okay, this well, it's a cloud. It's in this consensus space. It's about the spike. The main cluster are, and this in red. You may not see that. I mean, we may choose a better way to present it. But in red, what you are seeing is the 5% of images that, according to our measurements, are more differently mapped by a Cryo dragon and by Hetsiren. In the case of Hetsiren, they are here, the same images with the same CTF, with the same pose, whatever. They are in different parts of the space by a Cryo dragon. Okay, but they are rubbish. We understand that they are bad. Okay, we understand it. We take them, we go through cryospark homogeneous reconstruction, and we get a very nice one up. So they were not rubbish. So we have to still understand this result, but a very clear message is that we are in the road to understand flexibility and compositional heterogeneity and all that, but the road is still a little bit bumpy, and we need more time there. Of course, since we realize that, we are also sharing with people and having training on flexibility analysis. So we started in 23 with the first course on flexibility analysis. This is the last course, I don't know, 2 weeks ago or something like that. So, and well, it is going well, and we have normally a one-to-one session to know from the people attending the course which are the problems after being exposed to a variety of tools. And you may be wondering, what is this instruct thing? Well, another thing is that normally, well, all the courses we run it on the cloud, and now AWS, Amazon itself, is going to offer the software Scipion as part of its services already, and also SVGrid is going, especially for the pharma offer, is going to offer a Scipion on the cloud as a possibility for you to choose and just run there. This instruct thing is really, the hub is in the UK, in Oxford, and is about sharing infrastructure for structural biology, for integrative structural biology. There are many services, and actually one of them is about image processing, and specific. I mean, it has 2 things. One is general image processing, and the other is specifically about variability analysis. So if you have an issue, once you are analyzing the images and you consider that you may benefit from an extra processing of the images based on the variability with all these methods, well, possibilities to apply, to instruct for an access service. And of course, we run other courses. This is still, the application is still on, but this is the bread and butter single particle analysis, okay? This is not the flexibility thing. And of course, this is the work of many people. I have presented mostly the work of David, the work on a Scipion that is with Junior and with Jorge, and I have not presented molecular dynamics mixture, how to relate them with molecular dynamics, that is the work that James has been doing in the lab, and I have not presented other things related to non-AI methods for variability analysis, that is. But anyway, before, I think I am still on my time, so I take, Maya was asking yesterday about preferred orientation. And I didn't have the chance to make my question, but all these methods start from the assumption that you know the pose. And we may be able to not start from that position, but it is very difficult to get the pose right if you have preferred orientation. So this is bound to have problems. But on top of that, there is another problem, is that the information that you get in terms of understanding variability is going to be very different depending on the point of view you are looking at the molecule. So from that point of view, it's not only that these things are going to be sensible to preferred orientation, is that they are going to be sensible to orientation. And this is a way to make them less prone to be sensible to orientation, but probably we will find limitations. You also talked about putting a priori constraint based on biochemistry. I mean, models and things like that. We haven't done it here, but we are doing that in the one of the deformation fields. You have, Opus DSD is a method that really has put it, and really the answer there is one of those answers that is fantastic because you are putting a priori information, and this is hopefully supplementing your data. The bad part, you are putting a priori information, and you may forget your measurement if you don't do it the way correctly. So I think that energy landscape, okay. Well, with these differences, I would hesitate at this moment to go into that direction. But anyway, thank you very much, everybody, and thank you to acknowledge really the work of this group in this context. Thank you very much.
Questions from the audience?
Thank you, Jose Maria. Whether you use deformation fields or decoders, there's a lot of additional parameters that we use to describe our data. Now, with that comes a risk of overfitting. So in the methods you've described, the Het Siren and the Zernike 3D, do you keep your two half sets separate? Do you train two distinct decoders for each of the half sets? Because otherwise, I think there's a lot of scope to introduce the same problems we've had in the past on post determination, which is only 3 parameters per image. Now, I think there might be even more. So how do you deal with the risks of overfitting?
We do it at this, an obvious approach that we need to present it as part of the programming is to do in halves. The way we do it now is to run many times and to see the stability when you run. And now we can check in a simple manner the stability of different runs. That is something I have omitted. But with that, you can check that stability. Choice goes in many directions. Of course, the half set, we have to present it in a more open manner. But anyway, the number of parameters is huge. Not only because of the weight of the AI, is that do we choose to refine the positions or not? If we do, things would much better. Maybe are we overfitting? This is what we have to do with the half set and with now many runs of an approach and see the stability among runs.
More questions? So I was just going to quickly ask, so obviously I think this is amazing because I think it's very easy to be lured into this idea that everything's static, and you're clearly showing experimentally that it's not static and we can tease these out. How far is that away from sort of the biophysics, bioenergetics kind of approaches that we can apply?
The dream here is that really with this landscape, I mean, and Amit was talking about that yesterday. I mean, the density of a state could become connected to bioenergetics, and we would be really entering into a new area in which we would be using Cryo-EM for biophysics.
Mm.
The problem is that I think we miss still some confidence, at least at me, in our methods to get into that. But the way to put this in a broad context is that Cryo-EM has to go to quantitative biophysics with all the bias that any technique is going to have. I mean, the air-water interface is going to interfere with all that. But on top of that is that the methodologies still have to be refined a little bit more.
Okay. In which case, I'd like to thank all of the speakers for this morning. It's been some quite a variety of different themes to think about a bit more. Just for anybody who hasn't already checked out of the hotel, if you could do that before you grab your cup of coffee, that would be fantastic. And I wish you could all just join me in thanking all the speakers again for this morning. Thank you.
Thank you.